What's up, everybody? My name is Derek Gunther. I'm Senior Product Scientist with Ocean Optics, and I'm here today to give you a presentation called From Boxed Lunch to Beaker, a Spectral Tale of Leachants. And this is in collaboration with the Bye Bye Plastic Foundation. You can find their site at byebyeplastic.life. And they're a great organization. They promote all sorts of plastic alternatives, specifically in the music scene, so music festivals and clubs, things like that, but also just in life in general. So check them out. Before we start talking about the Leachants aspect, which is the main topic of the presentation, let's talk about the elephant in the room, which is, of course, microplastics. You hear about that constantly now in the news, right? So, and that's for good reason. That's something that's coming up as more correlative to things like dementia and other health issues that we see with more prevalence as time goes on. And this may be a hard fact to swallow, but you eat a credit card every week. What does that mean? So if you took a credit card's worth of plastic and ground it up into micro powder, nano powder, and equally distributed that through all the food and beverage that you consume in a week, that's what your body has to process right now in the microplastics that are just inherently in the food and water supply. So not just from what's leaching out from the food containers, but just what's coming from all the garbage that's shearing off all these microplastics, because you see garbage everywhere, right? So this is something that is totally new to human biology for the tens, hundreds of thousands of years of human history, but to every biology. You know, folks, I mentioned the dementia, microplastics are found, I think, in like 5 times higher concentration in the brains of dementia patients than those without dementia. But also we're seeing issues pop up in our pets, right? So dogs and cats getting cancers. And I'm not saying that this is the main cause. I don't want to be one of those people saying that, oh, this is what's causing this. I have no idea. I'm not a doctor. But if I had to put my money on it, it's probably playing a not insignificant role in one way or another in combination with other stuff that's going on. So this is affecting biologies all across, the human, the pets, and even the wildlife. You see this, the Conservancy folks that track all the wildlife health, they're seeing the increase in cancer rates. So there might be something there. I'm not saying I know for sure, but that's just something I might put my money on. Now, the Great Pacific Garbage Patch, if you're familiar with that, that's going to ensure that we're going to be paying the price for this for centuries to come, because it's the size of, I believe, France or some ridiculous scope. And every one of those bottles, and a lot of it's fishing gear, but it's just garbage from everywhere. Every time a wave, is just shearing those bottles against each other, they're shedding off microplastics. And it's going to be doing that forever, or for at least for centuries, and just kind of distributing that into the natural environment. And that gets eaten by, plankton, and then small fish, then bigger fish, then the ospreys and birds that then eat the fish, and that they die over land and get eaten by alligator. You know how that goes. It's Elton John's Circle of Life thing. So that's going to be happening and just working its way into our food and water supply for a pretty long time. So the long-term situation doesn't look very good. And one of the issues is that it's not a light switch scenario. The human mind wants to reduce everything to something simple to think about. So we like light switch type of rationale, where A then B, B then C. But it's not like that. This is going to be more like a death by 1,000 cuts rather than a guillotine, where everything's fine one day and then it's not fine the next day. This is going to be a gradual, just over time and space, where this is more and more of an issue, and it's harder to pin those down and get people to really take action on those. But let's not worry about tomorrow. That's all gloom and doom, right? Let's just have a picnic today with our plastic food containers. And I'm alluding here to what the study is going to involve. We can see the red Solo cups with this family here that's definitely not AI generated, and then the Tupperware that's holding all their foods and all that. But the situation And with these containers isn't much better news, because all of those plastics have inherently within them dyes and plasticizers, all this chemical gunk that's meant to have some sort of function that the manufacturer is aiming for, right? And that's what we're looking at in this study, where we looked at a range of common food and beverage containers, and we exposed them to water and ethanol for 24 hours to see what we could leach out of those, and then observe that with spectroscopy. So the 4 common food and beverage vessels that we checked out include the red Solo cup that you saw in the last slide, the Tupperware, a mason jar, and bioplastic. And this was bioplastic cups that were from the Bye Bye Plastic Foundation. That was kind of them to provide. And we exposed each of those, like I mentioned, to water or ethanol for 24 hours apiece. And then we scanned them with a UV system, ultraviolet, near infrared, and 785 nanometer Raman. And we scanned the before and after fluids. So the clean fluid that never saw any of these containers, and then the fluids that were exposed to the containers to see what leached out over time. Now, why do we pick water and ethanol? It's because different foods and different environments are going to pull out different chemicals at different rates. So we're going to see this, as you can imagine, ethanol being a solvent is going to want to pull things out more quickly and just at a higher quantity, and different types of things too. And this is true for oils, like olive oil is notorious for pulling different leachants out of certain plastic containers. Acids, if you're dealing with things that are acidic like citrus, right, lemonade and whatnot. Or on the basic side, the alkali water, pH 9.5, because it's so healthy and all that stuff. So all these different environments leach different things at different rates. And you'll notice also up here we have a little bit of a flow chart to show you where we are in the presentation. I found this is useful to let people know that they aren't going to be killed with death by PowerPoint. You can see where you are in this presentation, luckily. Here are a few photos from our test that we ran, or at least the experimental setup. So for the near-infrared scans here, we wanted to use a filtration technique, because you're going to see in the plots here shortly, the UV activity is much more pronounced. So UV is much more optically active compared to near-infrared signals just inherently aren't very active. So to get a usable signal, we figured we would take that bulk liquid and run it through a small filter and then compare that. So a filter that's been just filtered the clean fluid compared to a filter that was had the fluid, the leachant fluid filtered through it, and then comparing those with a reflection setup. So that's how we did for the NIR. Otherwise, we just looked at the liquid straight away using ultraviolet or Raman. And then this is one of our setups for 785 nanometer Raman. You can see the laser here and our laser and the test computer. And then this was the reflection setup, an example for the bulk material scan. So we did also look at the bulk materials because we wanted to see if those peaks that we were seeing in the fluid correlated to any peaks we were seeing in the bulk material naturally. So let's take a look at the ultraviolet results. This is the UV absorbance scans of those leachant fluids after 24 hours of water exposure. And you can see in yellow is the Tupperware, and that had the largest amount of leachant coming out of it there, very low. So you can see your eyes start around 370-ish. Everyone's a little different, but generally in this region is where you're starting to see stuff, and then up above here. But all this is invisible. So this is where you're not seeing it visibly, but it's there. And then the bioplastic is just behind it. But check out ethanol. Look at this. It's a night and day difference, as you would expect, right? So this is a solvent that's pulling out much more of those chemicals at a higher rate. And it's about 5 times increase. So this is like just above 0.05, and this is just below 0.01. So it's an over 5x increase for both the Tupperware and the bioplastic. So the Tupperware in each of these cases was the largest source of leachants in both the water and the ethanol, and the bioplastic was second place in each of those cases. But note the red Solo cup has a unique peak right here at right around 250, just shy of that, like 245 or so, where these are back here more in like the 220 range. Pardon me. So This is suggesting there's a unique leachant from the red solo cup that is different than what we're seeing coming out of the Tupperware or the bioplastic. With the near-infrared, there was no apparent signal when we did the water exposure, and I mentioned that it's harder to get those near-infrared signals out of samples, and just inherently. So that's why we used that filtration to amplify and pump up whatever we could. We didn't see anything with the water, but we did get a nice peak up here from the bioplastic, right around 2100 nanometers. So we'll see if that does or doesn't show up in the bulk material. But that again suggests a unique leachant that's present, and it's interesting because that's showing up, that's strong enough to show up in the NIR, which means that it must be very pronounced for it to have this much of a signal out in this kind of low activity type of region. Now, the bioplastic also had a unique peak in both the water and the ethanol when we ran the 785 nanometer Raman scans. So we were getting right around 1100 wave numbers. So this is in Raman shifts, which is wave numbers, not wavelength in nanometers. But right here we see it in the water and the ethanol, and it's actually more pronounced in the water, which is a little unexpected because ethanol does tend to pull things out more efficiently. So this was kind of a unique observation. Now, we also used a technique called SERS, SERS, that stands for Surface Enhanced Raman Spectroscopy, or Raman substrates, depending on who you're talking to. But this uses a nanostructure or nanoparticles to artificially enhance, that's where the E comes from in SERS, to enhance that Raman emission. So we're getting peaks that we can see that we wouldn't be able to see otherwise. It would be hidden in a normal bulk scan without the SERS effect. But most of them don't show anything. So none of these materials had any statistically significant activity except for the red solo cup. So we get this peak right around 2134. So there's something going on there that's at least SERS active from the red solo cup. And as we mentioned, we also scanned the bulk materials. We also scanned just the cups and Tupperware themselves with the UV, NIR, Raman, and all that to see if there were any correlative peaks. And for the most part, there weren't, except for the bioplastic had two big clear winners, or two big clear synchronizations between those. So we saw in the leachant fluid the 2100 nanometer peak in the NIR, which we also see in the bulk bioplastic cup right there. And we also saw that 1100 wave number Raman peak when we did that Raman scan there. And that's showing up likewise when we scan the bulk cup. So these are things that are very confirmable. You know, we see it in the cup, we see it in the fluid itself. So that lets us kind of dig down into specifically what chemical we're actually talking about. Now, the solo cup didn't show the 2134 wave number peak, which would have been like out here or whatnot, but that is probably because it's only a SERS active compound, and that does happen. That's the whole point of SERS. Like I said, it enhances things. So pesticides is a common SERS application, where if you scan an apple with a 785 Raman system, you probably aren't going to see the pesticide peaks that are on the apple skin unless it's like caked on there. You know, it's really, you can visibly see it. But if you were to take a SERS swab of the apple skin and it's only coated with like a ppm level of whatever pesticide, imidacloprid or something that's on there, I forget what they use for apples, but whatever you swab off of that, you're going to see those peaks even down at the ppm, ppb, sometimes ppt levels using that SERS enhancement. So if we aren't seeing it in the bulk material, that's not really surprising, because that's why we use SERS in the first place, is to pull those out. So what are the main takeaways on this? Maybe the first takeaway is that you are what you eat. And that's actually a misquote. It's a common phrase, but the original quote was from a physician, an English physician named Thomas something, it escapes me. You have to ask AI. Use your preferred AI bot to ask who originally said that. But that's not the original quote. It was, he said, "Tell me what you eat, and I will tell you what you are." And then over the decades and centuries or whatnot, that kind of boiled down and simplified into "you are what you eat." But that wasn't the original quote. But it is true, though, that we're and consuming more than we realize, and it has an effect on us that we may not realize or may not realize today, but we will one day in the future. For me, the hardest hitting graph when doing this data analysis was from the UV scans of the ethanol fluid, the leachant into the ethanol samples. And that was so dramatic with how large those peaks were and how distinct they were, especially for that activity that we saw very unique to the red Solo cup there. And, if you're using your plastics for liquor, if you're using a red Solo cup for, or Tupperware based polypropylene, something like that, for scotch or Everclear, heaven forbid, something that's really high proof, you might as well just be eating the container at that point, because you're getting a lot of stuff leaching into that fluid. So what is this stuff? We're talking about all these different peaks and bands showing up in all these different optical regions. So what are we actually looking at when we see those come up? For Tupperware is typically polypropylene, abbreviated PP, and that's usually going to be leaching out aromatic compounds, and that's a very broad chemical family, I know. So, but to get specific, we'd be on the lookout for butylated hydroxytoluene, abbreviated BHT. That's an antioxidant they use for to prevent degradation. So they want it to hold up mechanically and from UV rays and different things. And ergonox is also used for the same thing, and it's also an aromatic compound for that same purpose. The Solo cup is typically polystyrene. Solo cups are ubiquitous. They're everywhere. There's actually a new song, it's relatively new, a song by Armin van Buuren and W&W called Late Checkout. Look it up if you have a chance. And it references red Solo cups, and they're just ubiquitous. They're very culturally known globally. And they use polystyrene, which is polymerized styrene monomers. And if they aren't fully polymerized, those styrene monomers can shed and leach off into the fluid. So we're likely seeing some of that in addition to the plasticizers and residual solvents that are there. Again, that's very broad. But note that those are in orange, because that's going to come up in a second. Compared to the bioplastic, which has all sorts of stuff. We saw all sorts of activities that we weren't necessarily expecting, especially in the NIR, right? There was a lot of activity there, even though that's such a reduced activity band and out in the near infrared. But those things that were leaching out of the bioplastic include things, a whole group of aliphatic polyesters, including polylactic acid, polybutylene succinate, polybutylene adipate terephthalate, and those are all biodegradable, so they aren't as much of a concern. There's also the PHAs, those are polyhydroxyl alkanoates. I hope everyone's very impressed with my pronunciations on these. That's likewise biodegradable, and that's known to leach out those same types of monomers or short chain acids, and that's kind of expected from there. But again, though being biodegradable, they aren't as much of a concern. And also, like the red Solo cup, it has plasticizers and different agents in there, but they're typically things like citrates and glycerol, which are all benign things. And that's all to say that the things in orange are known to be toxic, persistent, and bioaccumulative. So they're accumulating in your body, like those drugs I talked about, that target specific areas in your body and then release the API at the beginning of the presentation. The bioaccumulative chemicals are kind of sticking around in your body, and those have their own set of toxins and things like that to them, as opposed to the bioplastic, which all of those things in green are known to be biodegradable, metabolically safe, and often food grade. So things like I said, citrates and glycerol, those are already things in what you eat, and they're naturally derived, so they're not that big of a deal. So this leads us to kind of two paths that can be taken at the same time. If we want to avoid the orange stuff there, or it's over on that side, so the orange stuff that's toxic and we don't want to be eating, there's two paths there. We can either go back in time to before plastics, before Bakelite. Bakelite was 1907 or 1909. Before that ever existed, everything in the world was either wood, metal, or glass, as in terms of containers and different uses in common daily life, right? So wood could then be turned into paper and pulp products, of course, and then metal and glass, but they're all very naturally cycling back into the environment. So For metals, for example, we mine ores out of the earth, which are salts, metal salts, and we refine them into the actual metals themselves. But then, let's say iron. We take iron ore, mine it out of the ground, turn it into iron or into steel. But then that rusts over time, right? It oxidizes with the oxygen, reacts with the moisture in the air, and it turns into rust, which is an iron salt, and then just kind of washes itself back into the earth. No big deal. Glass, for example, is just sand. You take sand off the beach, you melt it down, you can mold it into a glass container, and then if you smash it with a hammer for an hour, eventually you end up with a mound of sand again. And wood, you grow a tree, cut it down, turn it into some wood product, and then it just eventually, naturally, that cellulose-based products naturally degrade back into the earth. So those were very good for us for tens of thousands of years. That kind of got us to where we are. But that's not to say plastics aren't useful, especially in modern applications for medical and electronics. If you need an IV bag or electrical insulation, right? There's plastics that can do all that stuff better than anything else. So looking forward, these bioplastics, if we get smart with those, we can have the benefits of plastics, but using chemicals that aren't toxic and aren't having long-term detrimental effects. They're things that we can deal with. So that's just something to think about. Those are our two paths that we can do at the same time. We can go backwards and use wood, metal, and glass, and we can go forwards and use smarter plastics that are more benign for our everyday use. So thanks so much for your time. Hopefully this was somewhat entertaining and educational. There's a few references there for the things we talked about at the beginning. And this Joel Pett cartoon that I liked had all the different recyclables, and then for microplastics trying to jam the whole earth in there. It's unfortunately kind of where we are at the moment. But if there's any questions or comments or anything you'd like to engage, definitely reach out. Happy to answer any of those. And thanks so much for your time.